So today we started the third semester. We will talk about graphs and about depth of search algorithm. So what is graph? Graph is basically a set of circles and line segments connecting these circles. So you have some circles and you have some line segments connecting these circles like this. So that's the graph. These circles are called vertices and these line segments called edges. Very basic stuff. There are two types of graphs, oriented graph and unoriented graph. So this graph is not oriented. There are different types of graphs which are called oriented graph. In oriented graph you have the same thing, but each edge have a direction. So it's directed, it's undirected and directed. Something like this. So this is directed graph, this is undirected graph. Cool. And they both are actually important. So for some problems you have something like this, for some problems you have something like this. Basically, these graphs, like directed graphs, usually occur when you have some problem, when you have some system and the system have some states, and these are some transition from one state to another state. So like you're standing here and you can move here from this, you can you can move anywhere here. For example, you start here and then you move here, then you move here and so on. So this graph kind of explains how you can move from one state to another state. And when you have a undirected graph, it's usually when you have some relation between different objects. So you have some number of objects and these two objects related to each other. So it's like symmetrical stuff. So these objects are in relation. Both graphs are important. There are different algorithms for different graphs. Some algorithms can be used for both directed and undirected graphs, but some algorithms are made specifically for one of these types. Cool. Let's go. Now, there are two important characteristics of the graph: number of vertices and number of edges. So I will say I have n vertices and m edges. And when we will talk about asymptotics of the time complexity of the algorithm, we will use these two variables, not one variable like we did in previous lectures. So usually in the previous lectures we had only one characteristic, like n, number of elements. Here we have two basic characteristics, and we kind of want to discuss how the time complexity depends on these two variables. So usually time complexity will be a function of two variables. That's usually how it's working in graphs. I will assume two simple inequations. First of all, let's look on number of edges. If number of edges is very small, then your graph is not connected. Yeah. So if you want your graph to be connected, so you don't want it to split into several parts like this. Then number of edges should be at least n-1. So if connected. Usually if graph is not connected, you can just split it into several connected parts and then run your algorithm in each individual component. So I will usually assume that m is at least n-1. Not always, but like this. And let's look on the maximal number of edges. So if you look on the maximal number of edges, then if we don't allow to have two identical edges, like two parallel, if we don't allow a situation like this, so we say that every edge is like unique, then number of edges should be at most, for undirected graph it should be at most n-1 over 2, and for directed graph it should be at most n-1 like this. In both cases, it's big O of n squared, like this. So I will usually assume that m is at least n, and m is no more than n squared. And it will give me some little bit shorter formulas for the time complexity. For example, if time complexity, you have something like equal n plus m. Well, let's put big O here. Big O of n plus m. So you have some linear algorithm. I will usually simply say that is big O of m and say it is enough. No? Because m is greater than n, yeah. So you can replace this n plus m with just m, because this summand is bigger than this. Or, for example, if time complexity is like n squared plus m, I will simply say it's big O of n squared, because m is less than n squared. Yeah? Just for simplicity. Okay. Now, if you read the real papers about algorithms and time complexities, you will usually see notation like this, because it's a more accurate way to explain how the time complexity works. But I will usually just ignore all this unimportant stuff just to make all the formulas simpler. Okay. Cool. What's next? What's next? Well, let's start the first algorithm. The first algorithm will be very simple. We have the undirected graph, and it is not connected. So let's make something like this, and something like this. Let's go. So you have this graph. It is not connected, so it is split into several connected components. What is connected component? Common component is a set of vertices, and in this set you can move from any node to any other node. For example, inside this set of 4 nodes, you can move from any node to any other node using only these edges. Yeah. So you can start from here and go here, here, and move to these 4 nodes. This relation, like these 2 nodes are connected, is a equivalence relation, like, because it is symmetric, it is transitive, yeah. So all your nodes will be split in some like equivalence classes, right? And in each this equivalence class, you can move from any node to any other node. This is how connectivity works in undirected graph. In all undirected graph, connectivity is very simple. There are some components. These sets called connected components. Let's. So these sets of vertices called connected components, and the connectivity in undirected graph works very simple way. If you have 2 nodes from the same connected component, they are connected. If you take 2 nodes from different connected components, they are not connected. Very simple relation, right? So the first algorithm we'll discuss today is basically to find all the connected components. So we're given the graph, and we want to find all the connected components in this graph. Cool. Yes, you can do it using disjoint union. Yeah, if you remember the last lecture, first semester, we actually talked about one important data structure, which was union find. And you can use union find this structure to make this works. That's true. That's true. You can just take all the edges, call the union function for each edge, and then have these sets in individual sets in your union find this structure. That's true. That's true. We will make it faster actually, but that also works. That's a good question. Now, how I will store the graph before we start the algorithm? Let's talk about how to store the graphs in your program. There are basically 2 important ways how to store graphs in program. First way is pretty simple. You just make a matrix n by n, and for each edge you put 1 in the cell which corresponds to your edge. For example, let's take some graph. Let's take this graph. Let's put nodes. Let's see, 1, 2, 3, 4, and 5, and put some edges. Like this. For For example, for this graph, you can start like this. You can make matrix 5 by 5 because you have 5 nodes. Yeah. And now for each edge, you just put 1 in the corresponding cell. For example, here you have node 1, and node 1 have edge to node 2. So you take the first row, take second column, and put 1 here. So this one corresponds to this edge. And so on. For each edge, you just put 1 in the corresponding cell. So you have this edge from 3 to 2, from 3 to 1, from 4 to 2, 3, and 5. 2, 3, and 5, and from 5 to 3. Yeah. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Yeah. Check some more. And you just put zeros in all other cells, like this. This matrix is actually, sometimes it's useful because it's matrix, so you can run some algebraistics, like some algorithms from linear algebra just to work with this set of edges as a matrix. There are a lot of quite cool algorithms in linear algebra, you can apply them there. But we will usually not do it like this, just because this matrix is too big. This matrix uses n² memory, yeah? And if the number of edges is small, it's very ineffective. So we will usually use another approach how to store the graph. We will do it like this. We will store for each node, we will store simply the list of all edges connected to this vertex. For example, here we have like five vertices, so we will have 5 lists. So for each node we have a list. And in this list we will simply store all the edges going from this node. For example, here we have from node 1 we have edge to vertex 2. From 2 we have nothing. From 3 we have 1 and 2. From 4 we have 2, 3, and 5, and from 5 we have 4. So we have these lists. Very simple. So what is the total number of elements in all these lists? Well, it's pretty simple. So each edge only occurs in one of these lists. So total length of all these lists is just m. So here the total length is m, and size of this matrix is n². So if your graph is almost full, then you don't care. So if your graph is close to the full graph, so you have almost all the edges, then you have about n² edges, and you can store them like this. If you have small number of edges, so you have a sparse graph, so number of edges is much less than n². Then the preferred way to store graph is like this, because this uses just m memory and not n². If m is much less than n², then that's how you want to store your graph. Cool. What? 5 to 3? Ah. Okay. Let's fix this. I just get it from here. Nice. That's all. The same thing works for undirected graph. If you have undirected graph, you just make the same thing, but here you will have symmetrical matrix. So for each one, you will have symmetrical one in the corresponding cell. And here, each edge will occur twice. So you will have one edge from here to here. Here you have one edge. So for each node, in the list of u, you will have v. In the list of v, you will have u. So each edge will give you 2 elements in this list. But the idea is the same. Cool. Now, yeah, I believe that's all. So let's write the first algorithm. The first algorithm will just find you the connected components in the given graph. Yeah. Yes. If you have undirected graph, then you have these two elements, two ones in the same time. So if you have this adjacency matrix, you have one here and one here. This UV and this VU. Yeah. So you have two ones for each edge of your graph. Yeah. Cool. Now that's all. Let's write the first algorithm. The algorithm will works like this. You have your graph. You will take any vertex of your graph. Let's, for example, take this vertex of the graph. And now I will call the recursive procedure, which will mark all the vertices connected to this vertex. So I will start from this vertex and mark all the vertices connected to this vertex. So after I run this procedure, all the nodes inside the X-connect component will be marked. That's the plan. The algorithm is called depth search. DPTH. Yeah, first search. The algorithm is very simple. I just write the code here. So let's try this. DFS of node V. So this is the recursive procedure. It takes some node V and try to mark all the nodes connected to this node V. So I start from node V and try to mark everything connected to node V. So how to do it? It's pretty simple. So first we mark the node V. Now we'll simply iterate over all edges connected to node V. So we mark node V and then try to mark everything connected to node V. So we iterate over all edges for all VU. Let's call this list like out of V. So out of V is the list of all edges connected to node V. Yeah. So we take all the V. So we take all edges connected to node V, and now see. So you're standing in node V. You take all the edges. Here you take node U. If node U is not yet marked, so this is marked. Now we take the node U. If it is not yet marked, then we simply recursively go to this node U, mark it and everything connected to it. So simply call the DFS of node U. That's all. That's the whole plan. Pretty simple, right? Any questions by now? So this this is not the only representation of the graphs, but it is the two most common representations of the graph. There are other representations of the graph. They are used for some specific algorithms. We'll talk about this. If at some point we need some another representation, we will make it. These are just the two most common representations of the graph used for most algorithms. So usually we will use this representation. What's in on fork line? So what we're doing here, we take the list of node V, so we take this list, yeah, and iterate over all nodes in these lists. So this out of V is the list of all nodes connected to node V. I don't think you mark all the neighbors. No, I will mark from the neighbors. Yes, if you have a tree, you can do it simpler, but we don't have a tree here. We have some graph. Yes, if you try to run the face on a tree, you can do it without these marks. But that's not the point. Cool. Well, let's run from this node, for example. Okay, let's run from here. Let's just nodes here. Let's make 1, 2, 3, 4, 5, 6, 7, and 8, and 9. So what will happen in this algorithm if we run this procedure? Let's remove something. Let's remove this edge, just to make it more interesting. So we start in this graph. We have these lists. Let's just build these lists. So we have list for vertex 1. We have 4 and 5. For vertex 2, we have 9 and 8. For 3, we have 6. For 4, we have 1. For 5, we have 5 here. It's 1 and 7. For 6, we have 3. For 7, 1 and 5. For 8, 2 and 9. Almost fit. 2 and 6. 2 and 8. So for this graph, we have these lists. Yeah. Now, what will happen if we run this algorithm from the node 1? So we start from node 1. It will mark the node 1 and then iterate over all neighbors of the node 1. So we have 3 neighbors. So we're staying here. I forgot something. 4, 5, and 7. Yeah. Yeah. So we start from node 1 and try to iterate all neighbors of node 1. Take the first element, it's node 4. So we go to node 4. And recursively try to find everything connected to node 4. So we recursively go here, mark this node 4, then go back. Because now from node 4, we do the same thing. We mark node 4, then iterate over all neighbors of node 4. So we take this node 4. It has only one neighbor, node 1. But node 1 is already marked. So in this 4, we iterate over all nodes connected to node 4. It's only node 1. It's already marked, so we don't go here. So this 4 ends, and we go back from the recursion back here. Now from here, we take the next node. Next node is 5, so we call DFS of 5. From here we try to go here, then go back. Now we go to node 5. Node 5, here it is, has 2 neighbors, 1 and 7. Node 1 is already marked, node 7 is not yet marked, so we go to node 7. So from here we go to node 7. Node 7 have 2 neighbors. Here it is. Node 7 has 2 neighbors. They both are marked. So we don't go anywhere. The recursion ends. We go back to node 5. Node 5 has no more neighbors. So we go back to node 1. Node 1 has neighbor 7. It's already marked. So that's all. That's the whole recursion tree. That's all. So by the end of this procedure, everything connected to node 1 is marked. So this node is marked, this node is marked, this node is marked, this is marked. Now, how to find the second connected components? We take the next node, which is not connected, not marked yet. So we take any node which is not marked. For example, node 2. So we start from node 2, called DFS from node 2. And do the same thing. So we start here, go to node 8, so mark this, go here, mark this, go here, mark this, nowhere to go, nowhere to go, nowhere to go, that's all. Go to DFS of 8, here we have to DFS from 9, then go back, And in the end, we do the same here. Okay. That's the whole plan. That's the whole plan. Now we need two things to prove. First, we need to prove that this algorithm actually works. And second, we need to prove the time complexity. Let's go. First, let's prove this algorithm actually works. So how to prove the algorithm actually works? It's actually quite obvious because it's a pretty simple algorithm, but I will try to prove it with a little bit of mathematics just to show you how these algorithms are usually proved. So let's prove this algorithm actually works. So what I want to prove, if I start DFS from some node, by the end of this procedure, everything connected to this node will be marked and nothing else will be marked. So if I have some node V, it belongs to some connect component, then by the end of this DFS, all the nodes in this connect component will be marked and nothing else will be marked. That's basically what it means that I will mark all the connect component, right? Well, first of all, let's prove that everything that will be marked by these algorithms is actually connected to node V. So I want to prove that if some node U is marked, to V, U is marked. Yeah. Like this. So I want to prove that all the nodes connected to V are marked and vice versa. Let's prove from left to right. Let's prove from right to left. That's simple. That's simple. Let's prove that everything what was marked by this algorithm is actually connected to node V. No. We'll talk about time complexity in a second. Let's prove that this algorithm actually works, because if it doesn't work, it does make sense. What's the time complexity? First, we need to prove that the algorithm is correct, right? Let's prove this. It's simple. So first, let's prove that everything which is marked is connected to node V. It's simple. Let's prove it just by we maintain the invariant that everything marked is connected to V. So if we run DFS from some node, let's say U, then just by invariant, let's call it S, because we have V here just. So S is the first vertex from which we start the DFS passage, right? So this is the first node. So if I run DFS from node S, then everything connected to S will be marked. Let's see. So I have node S, and I have this node, let's say V. Just by invariant, I say that this node is marked. It means it is connected to node S. Yeah? We just maintain the invariant that everything that is marked is connected to node S. Now let's see what happens in this procedure. In this procedure, we iterate all edges from this node V, take this node U, recursively go here and mark this node. If we go here and mark this node, it means this node is connected to node S, because this node is connected to this node and this is connected to S. So just by transitivity, so this U is connected to S. That's all. So we simply maintain the invariant that every node which is marked is connected to node S. That's all. So we proved this side, right? So now let's prove the opposite. So let's prove that if something is connected to S, it will be marked by this algorithm. That's a little bit more complicated. So we have some node S, yeah? And we start DFS from this node. And there is another node U. Okay, U. We have some node U, and this node is connected to S. So there is some path which connects S and U. Let's prove that if we run DFS from this node S, this U will be marked at some point. How to prove this? Very simple actually. Node S will be marked. Yeah. Well, because we start DFS from node S, like the first action here will be to mark node S. So the node S will be definitely marked. Well, let's see, if the node U is not marked, then let's look on this path. On this path, let's find the first node which is not marked. So we start from node S and go down until we find the first node which was not marked. So from here, this is marked, and this is not marked. So we have these two nodes. Let's say node X and Y. Yeah? So on this path from S to U, we have some node X which was marked, and some node Y which wasn't marked. Now, let's see why this happens. That's kind of strange, because if we mark node X, then it means we only mark nodes here. So if we mark this node X, it means we at some point run this recursive procedure from node X. But when we run this recursive procedure from node X, we iterate through all edges connected to node X. So we actually look at this edge. So we actually found this edge. And if we found this edge and this node wasn't marked, it means that we must go to this node Y and run the DFS from this node. So this situation must not happen. That's all. That's a contradiction. So it means that if some node U is connected to node S, then at some point it will be marked by this algorithm. Yeah? Is it clear? How can we do DFS iterative? We'll talk about it in some practice. It's not very important. Every recursive algorithm can be made iterative just by manually making the stack of recursion using stack. So if you have some recursive algorithm, you can just remove the recursion and manually make this stack of the recursion and make the non-recursive algorithm. But it's just recursion is just a simple way to explain how the algorithm works. If you have some algorithm with stacks, usually it's much easier to explain how it works using recursion. But recursion is not the fundamental property of the algorithms. Recursion is just a simple way to explain how the algorithm with stack works. That's all. Cool. What I forgot? Time complexity. Let's talk about time complexity. What is the time complexity of this algorithm? No, let's see. Time complexity, this is the recursive algorithm. To calculate time complexity, we need to calculate total time complexity of each recursive call of this algorithm. What is the total number of these recursive calls? Well, for each node, we will call this DFS function only once. Because we only go to the nodes which wasn't marked yet. And when we go into this recursion, we mark this node by the first operation. Yeah? So we only call this DFS function for each node exactly once. Now, what happens? So let's just write this. So we do it once for each v. So for each v, we will call this DFS only once. Now, what happens inside this DFS? We iterate through all edges connected to node v. What is the total number of all? So what is the total length of all these lists? Total length of all these lists. So for each list, we'll iterate through all elements of this list, right? So total number of elements of this list again is n. So the total time complexity of all these loops is m. So total time complexity is m. Yes, it's n plus m again. Time complexity is n plus m, but I will just ignore this plus n because I also assume that. Okay, let's just for simplicity. You also need to make these separations. These separations you need to make n times. I usually ignore this plus n because I assume that m is greater than n. In this algorithm is actually not good because this graph is not connected, but usually I just ignore it. Cool. So that's all. That's the depth of search algorithm. Nice. Isn't list is n size? No, the total size of all these lists, sum of all these sizes, is m, because for each edge you have the element in two lists. So no 2m. Okay. No, you have n lists. You have n lists, but total size of all these lists is m. That's what I mean. Cool. Now, that's the first application of the depth of search algorithm, but it's not the... If it was the only application of the depth of search, it will not be so interesting. So we'll discuss a lot of different applications of depth of search algorithm. Like these lectures and few next lectures, we'll discuss only the depth of search algorithm. It turns out it is actually quite important algorithm for the graphs, for both directed graph and undirected graphs. So we'll discuss a few different algorithms which are based on depth of search algorithm. Cool. So today the first algorithm we'll discuss, the next one, this was the first. The next algorithm we'll discuss is actually working on directed graphs. So let's talk about directed graphs. Phone is ringing. Okay, I hope it wasn't important. Let's just put it on. It's the start of the semester. Everybody's calling like 10 times a day. I hate the Septembers. Directed graphs. So imagine you have some directed graph. Let's put something like 3 to 5 to 2, and here's 1, and here's something else like this. Yeah. Wake me up when some time runs. Okay, so I think Billy Joy is kind of teacher in some university. That's interesting. It's an interesting thought. I didn't think that this song was about universities. Interesting. What I was talking about. So you have directed graph. So you have a directed graph. Very important case of directed graph is a cyclic directed graph. So if you have a cyclic directed graph like this, a cyclic means it doesn't have cycles. So if you don't have any cycles in your directed graph, that's very important case of directed graphs. One of cool things what you can do when you have no cycles, you can make something that calls topological ordering, something about topological sorting. Topological sorting. Topological sorting means you have some order of the nodes, and if you put the nodes in this order, all the edges will go from left to right, basically. For example, here you can put node 3, then let's say node 4, then for example 5, then 1, and then 2. So if you put the nodes in this order, then all the edges will go from left to right. We have 3 to 4, 3 to 5, 3 to 1, 4 to 1, 5 to 1, and 5 to 2, and 1 to 2, like this. A cyclic graph is a tree. The term acyclic graph usually used when you have directed graph. If you have undirected acyclic graph, it's just a tree or a forest or something like this. So it's not that interesting. So this term is usually used for directed graphs. Yeah. Now, let's talk about this topological sorting. What is the meaning of this topological ordering and why is it important? For example, you have something like, I don't know, you have some libraries, yeah, and you have some dependencies. So each library depends on some another libraries, and you want to load these libraries in some order such that when you load some library, all the dependencies are already loaded, something like this. This is actually how it works, yeah. So what you can do, you can make this topological ordering, and it gives you the order in which you need to load your libraries. Yeah? So you load libraries one by one, and each time you load library, everything, all this library depends, actually loaded before. No, it depends. If this is dependencies from right to left, it doesn't matter. So. Another thing you can do when you have topological ordering is to make different dynamic programming algorithms. So, for example, we discussed in first semester some dynamic programming algorithms. You can do it on a cyclic graph if you first make topological ordering. So first you make topological ordering of your graph, and then you write dynamic programming like from right to left or left to right. It depends. Since all edges go from left to right, when you calculate some value here, these three values are already calculated. So you know these three values, so you use these three values to calculate value here, and so on. So all the dynamic programming algorithms may be done on this cyclic graph, and if you first start making the topological ordering of the nodes of this graph. So that's why it's important. Cool. Yeah. So now let's know how to make this topological ordering. There are two ways to make topological sorting, and both ways are actually important. So I will just explain both ways. Okay. The first algorithm is very simple. Let's just take this depth first search algorithm, and in the end of this depth first search, put the node V into the list of topological ordering. So in the end of this depth first search here, just add node V to topological ordering. Let's make example this top sort. Very simple. That's all. Now I claim that if you run it like this, then you will get all the nodes from right to left in this order. So for example, let's run from here. So if you start the FS from node 1, here you go to node 2. So you mark this. You mark this, you mark this. Then it's nowhere to go from this node 2. So you output this node 2 into your list. Let's put it here. Then you go back. There's nowhere to go from node 1. So you output node 1. That's all. Now you take any not marked node. So you take node 3, for example. Start from here, go to node, I don't know, 4. So you start from here, go here. There's nowhere to go from node 4. So you stop the recursion, you output node 4. Now you go back here. You see another edge from 3 to 5, so you go to node 5. Mark node 5. There's nowhere to go from node 5, so you stop the recursion there. Output node 5, then go back to node 3. Nowhere to go from node 3, so you output node 3. So this is topological ordering. It's another topological ordering, yeah? So you have one topological ordering. So the topological ordering is not unique. They may be different topological sorting of the same graph, but it is the correct topological sort of these nodes. So you need an outer for loop. Yes. So this is the recursive procedure. In your main procedure, you need something like this. You need to iterate for all nodes from 0, let's say, to n-1. Here I enumerate from 1, but usually in your program you start from 0. And see if it is not marked, then you call DFS, like this. Actually, what you can do, if you just want to run one DFS, you may add another node here, so some node 0, and just connect this node to all nodes of your graph, like this. And then you can just run DFS from this node 0. So here you will just DFS from node 0. And it will automatically run all your DFSs. That's another way to implement the same algorithm. It's actually not bad. In theory, this is the easiest way to get rid of all these extra loops. In practice, this is the easiest way to do it. Just make one more loop and just iterate all nodes and run this DFS several times. Up to you. Okay. Do we have any more time? Oh, we have a lot of time. Cool. Let's prove. I claim that if you do it like this, then as the output you will have some topological ordering. Let's prove this. How to prove that something is topological ordering? You need to prove that all edges go from left to right. So let's take some node. So let's take the node V. Let's look on all edges going from this node V. So from this node V, you have some edge to node U. We need to prove that this edge goes from left to right. So vertex U must be added to this list before node V. Why is this true? Well, because in this loop, we actually found this edge. When we found this edge, we first go into recursion for this node U, run DFS here. Then, when we end this DFS, we added this U to the topological ordering, and then we go back and added node V to the topological ordering. So node U was added before the node V. That's almost true. Can you see what's the problem here? Again, I claim if you have edge from V to U, then in this loop, you will find this edge from V to U, run DFS from node U. In the end of DFS, so it looks like this. So you have DFS of node V, then you run DFS from node U. Then when you finish this recursion, you add U to topological ordering, then you go back and then add V to the topological ordering. So node V will be added after you added node V. Yeah. If we don't visit V at all, but visit U. Yeah, it may happen. Then no, we visit all the nodes. So it may happen that we visited node U before we visit node V. So we may visit node U in some. So we start from this S. So we first go here, mark this node U, then go back, and then here we visit node V. So when we visit node V, node U may be already marked. So when we see this edge, we don't go into this recursion because U is already marked. Let's prove. I claim that in this case, vertex U is already in the topological ordering. So if we see this situation, so we stand here, we see this edge, then U, for this node U, this recursion already finishes, and we already added this node U to the topological ordering. So the situation looks like this. We first go to node U, finish the recursion, then go back, and then go node V. That's the only situation that can happen. So if it is like this, then this U is already in the topological ordering, and it's added before the node V. Do we need to reverse top sort list? Yes, we need to reverse top list. This top sort list will be formed from right to left. Yeah. If you want to correct the topological ordering, you need to reverse this list in the end. Yeah, that's right. But what if for this node U it's already marked? So we have the operation mark the node and add the node topological ordering. What if for this node U we already marked this node, but we didn't add it to the topological ordering yet? So what if this node U is in some middle state? So for this node U, we already marked this node, but we still didn't add it to the topological ordering. Let's see if it may happen. So let's see if it's possible for node U to be marked, but not put in the topological ordering yet. Well, let's see how it may happen. If this node is marked, but is not put in the topological ordering, it means for this node U, we are here something, yeah? So this node U is in the recursion zone. So when we look on the node V and find this edge, this node U is in some middle state, is something here. It means it is in some recursion. So it's somewhere here. So we start here and there's something else, and then go here. This is U. What does it mean? It means we start from node S, then somehow we go to node U, and then from node U we somehow go to node V, like this. But it means we have a cycle. Yeah. So we have a path from U to V, and then we have edge from V to U. So we have this cycle in our graph. And if we have cycle, we obviously can't make topological ordering. Should we prove it? Yeah. This is the proof. Yeah. So if you have cycle in your graph, you can't make topological ordering, because if all edges go from left to right, you can't make a cycle. At some point, you need to go from right to left. That's all. Okay, so I just proved that for each edge VU, node U was added to the topological ordering before node V, if the graph is acyclic. So if you don't have any cycles in your graph, then this algorithm will give you the topological ordering. Now, if you have cycles, you cannot make topological ordering, obviously, yeah? Because all edges go from left to right. You can't make cycles when all edges go from left to right. Right. Well, if you think about think about dependencies, actually, that thing which happens sometimes. So you have dependencies between some operations, and from this library you have this dependency from this, and then you have cycle. It usually ends badly. So when this happens, it means you can't load any library because they have the cyclic dependencies. That happens if you have a bad bureaucracy in your country. It happens sometimes in Russia. So you go somewhere and they send you to another organization, and then you send to another organization, and then you have a loop. So you just from here you go here, from here you go here, and then you cannot make anything because we're just sending you in a cycle. Any more questions? No. Okay, so this is the first algorithm of how to make topological sorting. The deadlock is basically the same thing. Yes, if you may have some when you have parallel algorithms, you may have situation like this. Yeah, so you have a few threads. Each thread waiting for another thread to finish before it can continue. So if you have a cycle in this graph, then you have a deadlock. Yeah. Now, That's the first algorithm. Another algorithm is also important. Another algorithm is important. It works like this. Let's take the graph. Let's take the graph and just look at it. We want to make a topological ordering, so we want to make this ordering. Let's think what vertex may be the first vertex in this order. So let's try to find this leftmost vertex in the topological ordering. This leftmost vertex must be a vertex which don't have any incoming edges. So we need to find a vertex which have no ingoing edges. Yeah. Detecting cycles. We'll talk about detecting cycles in a minute. Yeah, I remember about this. Yeah. So I'll just explain another algorithm because it's also important. So let's try to build this topological ordering without any DFS. So the algorithm is very simple. Let's try to find the first vertex in topological ordering. It must be the vertex which doesn't have any incoming edges. Yeah. So let's find any vertex which have no ingoing edges. In our graph, this node is free. So let's take node 3 because it doesn't have any ingoing edges, and put this node as the first node in our topological ordering. And now simply remove this node from the graph. So we just remove this node from the graph. Now from the remaining 4 vertices, let's pick any vertex which has no incoming edges. So for example, we have 2 vertices. We have node 4 and node 5. Yeah? So we have these 2 vertices have no ingoing edges. No, since we remove this, yeah. If we remove this node 3, these 2 nodes have no ingoing edges. So we just take any of these 2 nodes and put them in the next position in this list. For example, let's put node 4. And again, remove it from this list. Now you have these 3 nodes. From these 3 nodes, you have this node 5, which has no ingoing edges. So we take this node 5, put it in the next position, so on. So every time you just take any node which has no ingoing edges and put it in the next position and remove it from the graph. That's the whole algorithm. So let's try to implement it. So what we need to do, we need to maintain a set of vertices which has no ingoing edges. And now each time we take one of these nodes and try to remove it from a graph. When we remove it from a graph, we need to iterate all edges connected to this node and remove these edges from the list of this node. So we need to maintain 2 operations. First operation is to find any node which has no ingoing edges, and the second operation is to remove the edges connected to this node. What data structure can we use? This data structure is very simple. We will simply maintain the counter for each node. For each node, we will remember the number of edges which are going into this node. So, for example, in this graph, we will maintain this counter. So let's see, 1, 2, 3, 4, 5. So for each node, let's calculate the number of edges going into this node. So for in node 1, we have 2 ingoing edges. For node 2, we have 2 ingoing edges. For node 3, 0. Here we have 1, and here we have 1. So let's simply maintain this array of counters. Yes, you can use priority queues as well, but priority queue will give you another log n factor in your time complexity. You don't want to have another log n factor. You can do it in linear time. 3, 5, 4, 1, 2 is also topological ordering. Yes. 3, 5, 4, 1, 2 is also topological ordering. Yeah. Yes, you can. Now you need to maintain the set of zeros. Yeah. So you can maintain a set of zeros. First of all, it will contain only node 3. Yeah. So I will maintain this array of counters and the set of vertices with counter equal to 0. Now, each time what I need to do, I take some node from this set put it into topological ordering. Again, let's erase this. And then try to erase it from graph. When I erase node 3 from graph, I iterate over all edges connected to node 3. So I have these 3 edges to 1, 4, and 5. And just decrease these 3 counters. So I decrease counter for node 1, for node 4, and for node 5. And when I decrease counter, I see if the counter became 0, then I put this node into this list. So I decrease these 2 counters, now they are 0, so I can put these 2 nodes into this list. So put it 4 and 5. Now again, you take any node from this list, for example node 4, put it into topological ordering, then iterate over all edges connected to node 4, have only one edge to node 1, decrease this counter. It was 2, yeah, it was 2. Have 2 incoming edges. Yeah, right. So now you find this edge, so you decrease counter for node 1, it is now 1, and so on. So you take this node, put it here, decrease counter for nodes 1 and 2, so here is 1, here is 0, see this 0 added here. Now you take this node, put it here, iterate over this edge, decrease this counter, put this here, and so on. Yeah, take this node, put it here. Well, how to print all possible top sorts? There is an exponential number of topological ordering, obviously. Well, if you have graph like this, for example, there is n factorial way to. So even if the graph is connected, there may be exponential number of topological orderings. So you don't want to print all of them. To calculate the number of possible topological ordering is something like p-space connected, p-space complete, something. I'm not sure, but no. I don't know the correct term for these problems, but it is kind of hard problem. You cannot calculate the number of. You can calculate the number of topological orderings in polynomial time. Sadly. So there may be many different topological orderings. You cannot output them all, and you cannot calculate the number of them. So it's not in P hard because it's not yes/no problem. There are special classes for these problems when you need to calculate something. I forgot how to call them. There are special terms for problems when you need to calculate something. Usually, for NP problems, you need to answer yes or no. Yeah, so it's different classes. It doesn't matter. Doesn't matter. Let's write the code. I forgot my watch. Nice. So let's write the code for this algorithm. So the algorithm is very simple. So for each node we calculate the number of ingoing edges. So let's make this counter. So counter for node V is number of ingoing edges. Yes. And 0 will be the set of zeros. Now first let's put all the zeros. So we iterate all nodes. So if counter is 0, we just put the node I into this set. Then, while this set is not empty, like this. Good enough. So while this set is not empty, we just take any node from this set. Let's take V as get. And iterate over all edges connected to this node. So we iterate over all edges going from this node V and decrease this counter. If it is 0, we add it to node to the set. Put, okay. Something like this. Now, let's talk about time complexity of this algorithm. What's going on with time complexity of this algorithm? Here, again, every node will be removed from the set C only once. So this works only once for each V. Yeah. So each vertex is removed from from the set Z only once. So when you remove the V from from the set, you iterate through all edges here. So again, for each node V, you iterate through all edges connected to this node. So the total number of operations here again will be linear. So total time complexity will be again n plus m. Okay, so both these algorithms are linear. So we have two algorithms with linear time complexity. Yeah, we did talk about this also. What data structure can you use to maintain this set Z? Yes. To maintain this set Z, you can use basically any linear data structure. Like you can use queue, you can use stack, you can use anything you want. I don't know what else you can use. I don't know. You can use linked list if you love linked lists. So for this set Z, you need to make these two operations to work in constant time. Yeah, you have these two operations. You have set. You want to have two operations: put element into set and get any element from the set. You don't need to care about the order of these elements. So you just put. You can just use stack here. You put element into stack, and here you pop top element from the stack. Or you can use queue or anything. Anything will work. We'll talk about dynamic programming in the end, okay? Nice. So that's all. That's how you build the topological ordering of your graph. Now, the next thing I need to talk is how to check if your graph is actually acyclic. So, topological ordering only exists when your graph have no cycles. And how to check if your graph has no cycles? That's interesting. Because sometimes you may actually be given some graph which has a cycle. And you kind of try to build topological ordering and see that it's not working. So how to check if your graph contains any cycles? Two ways. First way is very simple. You may just run one of these algorithms and see if it works. So, for example, for this algorithm, what will happen if your graph contains any cycles? We just write this algorithm. But for this algorithm, what will happen if your graph contains cycle? Any ideas? Well, let's try it random. So, for example, here we have node 1, here we have node 2, 3, and here we have cycle. It will not break. So there's nowhere here to break. What will end? What do you mean by break? What? Yeah, it will stop after the first. So it will end. Add this node 1 to the list, then remove it, and now the set Z is empty. So it will stop after ending. So it will add some nodes to the topological ordering, but not all of them. So you can check in the end if this topological ordering. I didn't add it. So let's here. Top sort add node V. Yeah. So if in the end this topological ordering has not all elements, it means we have some cycles. we can start. Sometimes we can add some nodes, because first we add some nodes from left to right. But at some point, if we have cycle, we cannot add any nodes from this cycle to our topological ordering. So at some point we will stop, because this set will be empty. So if we stop this algorithm before we added all the nodes to the topological ordering, it means that we have cycle in our graph. What will happen to this algorithm? It will actually never stop. It cannot stop. So if you have cycles and then you run this algorithm on your graph, it will build you some topological ordering. It will try at least. Okay. So this algorithm doesn't care about all this stuff. So it just tries to build topological ordering, and it will put all the nodes in the topological ordering, even if you have cycles. But how can you check if you have cycles? You see, this algorithm will put all the nodes into this list, because you run DFS from each node. So each node will be in the end put it into this topological ordering. How to check if you have cycles? Yes, simple way is just to check all the edges. So you run this algorithm, then look on this list and check that all edges go from left to right. If all edges go from left to right, then you have correct topological ordering. If you have some edge going from right to left, it means you had some cycles in your graph. Good. Another way to check if your graph contains cycles is simply by checking the situation we discussed before. So how check if you have a cycle? So if you have some node V and it has edge to some node U, and this node U is marked, but yet it wasn't put into topological ordering. So if for this node U we already marked this node, but we didn't put it in topological ordering, then we have cycle. We can check the situation. We can maintain for each vertex, we can maintain like 3 states. So each vertex has 3 states. State before we enter this recursion, state when we are in the middle of this recursion, and state when we are after the end of this recursion. So we maintain 3 states for each node. And if this node U is in the middle state, so we're standing here in this recursion for node U, it means we have cycle, because we started from node S. Again, for this U, we are in the middle of recursion, and here we entered the node V. So we have cycle here. If you have situation like this, then you have a cycle. Cool? Nice. Okay, now let's finally draw the important picture, and then this is the final thing for this lecture. I'll draw you one more picture just to show you what actually happens when you run the DFS such a way. Natively checking all edges NM. You just make the list of all edges, and for each edge you check if it is correct. So it's linear, yeah. So you just for each edge you can make numbers for each node. So you just for each vertex you remember the index of this vertex in this order, so you can check each edge in constant time, right? So you build this topological ordering. Just remember the indices of all nodes. Then you take 2 nodes, find their indices, and check if this index is less than this index. So you can do it in constant time. Cool. Final picture. Let's see how the whole situation works when you run depth first search in directed graph. So if you have some directed graph, then you start your DFS from some node, and you go here, you go here, you go here, let's see, and somewhere here, and then you go here, so like this. So let's say this is the tree of the recursion when you call DFS from this node. So you call DFS from this node, And these are all the edges which are used when we run this DFS. So you start from here, then you recursively go here, and so on. Then you go back, then you go here, back, go here, back, then go here, then go back, go here, go back, and so on. So this is the tree which is formed when you take on the edges which you used here when you call your DFS algorithm. So this may be not usually it is a forest, yeah. So usually you start from another tree, so usually it happens like this. So usually you have a forest, yeah. So you call DFS from here, it visits all these nodes. Then you call DFS from here, it visits all these nodes. But again, you can add one extra node here. So you can special node 0 and just connect it to every node. So instead of a forest of trees, you have a single tree. It's usually more convenient way to do it. Okay. Now let's look on this tree, and let's look on all other edges which can be in your graph. So these are all the trees, all the edges which were visited when we run this deep perception algorithm. Now let's look what other edges may exist in your graph. So let's take some node. Let's go from here. So let's take some node, for example, this. Can we have an edge which connects some ancestor to some predecessor like this? Can we have an edge like this in our graph? No, it's not that we can. So it's possible to have edge which connects some ancestor to some predecessor in this tree. Yeah. Look how can it happen. You start your depth first search from here. You go here, then you recursively, you first select this edge. So you go here, then you go back, and when you go back, you see this edge, but this node is already marked, so you don't use this edge. So beside these edges in your graph, you also may have edge which connects some ancestor to some predecessor. Can you have other situation? Can you have some node which connects some predecessor to some ancestor like this? Any thoughts? Yes, we can. Yeah. And actually, we will have these edges if we have at least one cycle. Because for each cycle, they must have an edge like this. Yeah. If the graph is acyclic, then we don't have it. Because each edge like this gives you a cycle. But if you have cycles in the graph, you will have edges which goes like this, from predecessor to some ancestor. Cool. And finally, you may have edges like this, which connects like this, from right to left. This is also possible. Yeah. So first you go here, mark all these nodes here, then you go to this branch, and then see this edge. But this vertex is already marked, so you see this edge, but you don't use it in your depth search. Let's try another here, like this. What you can't have in your graph is the edge which goes from left to right. So you can't have edge like this. No, because if you first visit this node and then you exit your recursion, it means this is already marked. Because if you're standing here and you finish your recursion, it means you already iterated all the edges. So you already saw this edge, and if this was not marked before, then you just enter the recursion. Yeah? So you can't have edges from left to right. That's, by the way, another explanation why the top sort algorithm works. So if you look on this situation, so if you don't have any cycles, it means you don't have any red edges. Yeah. So these red edges give you cycles, and only them actually. So if you have one of these red edges which connects predecessor to ancestor, then you have a cycle. if you only have these blue and green edges, I'm not sure if you, yes, you see the colors, right? So if you only have edges of type like this blue one connects to answer preset, like we have more like let's. If you have only edges of this and this type, so you only connect some answers, some predecessor, and some right to some left, then you can't have any cycles. No, it's easy to prove. This blue edge can give you a cycle because these two nodes was already connected. Yeah, because you have this path, so this edge that doesn't change the connection relation to them. Yeah? They already were connected, so you have this path from here to here, so this edge can't give you any cycle. These green edges also will not give you any cycles, because all green edges go from right to left. That's all. No, that's an important picture just to think about how your graph looks when you run the depth first search algorithm. So basically, your graph looks like this. You have this tree of depth first search, no, actually forest of depth first search. If you add this one extra vertex, then you have tree of depth first search. Yeah, you have this tree of depth first search, and you have some extra edges. Extra edges may go down. They may go up if you have cycles, and they may go from right to left. That's all possibilities. That's basically this picture we will use in some future algorithms when we will try to build something more complicated than just topological reasoning. We will basically use this picture to explain why the algorithms works. Yeah, if you listen to the previous semester, you may know how to check the type of your edge. So if you look on some edge, how to check which type of these edges. So how to check if this edge goes from top to bottom, from bottom to top, or from right to left. Any ideas? In the previous semester, we discussed a lot of tree algorithms. So you may simply want to check what is the type of your edge. So there are three types of edge: going down, going up, and going from right to left. How to, by entry and exit time, yeah, right. So if you just, in this depth first search, remember the entry and exit time for each node. So basically here, what you want to do here, remember that in of v equal to, let's say, t++. And here you say out of v equal to t++. So remember the time when you enter the node and time when you exit the node. So if you remember these two things, you can see the relations between these two nodes in this depth first search tree. For this green node, for this green edge, you will have something like this. If you have this node, you enter this node and exit this node, then you go here, you enter this node, exit this node. So if these two segments do not intersect, then you have a situation like this. For this blue edge, you have this parent, so you enter the parent, then you enter the child, then you go back, exit the child, exit the parent. So if you have a situation like this, then you have this green edge and so on, the blue edge and so on. Just by looking on entry and exit type of each node, you can basically see which type of edge you see now. Okay, this is just some preparations for future algorithms. In the future, we'll basically think about this more trying to use these to build more complicated things. Okay, I think it's enough for today. Thank you for joining me. We need one cat on cat. Let's make sense. Okay, let's move the cat here. Now it's better.